Specifically, I will talk about all the activity we had at Links since last workshop last year. Okay. Okay. So thank you, Sebastian. So yeah, last year I presented some what we were doing on quantum computing and networking and communications at Links, and here it's a kind of update to see for all of you to see what happened in 1 year on this topic at Links. So as an introduction, what is important to know is that it is related to what we call the second quantum revolution. And so the first one, to understand what is the second, you need to understand what is the first one, the first quantum revolution. It is about manipulating assemble of quantum particles, but as a group, not individually, and with their interaction. And so this is about statistical behaviors of this kind of particle assembles. And this leads to technologies that are nowadays very mature, such as transistor, lasers, and many other ones. The second revolution is more about manipulating individual particles and with their quantum properties, such as superposition and quantum entanglement between two particles or several particles, but really considering particles as individual systems interacting together. And so my talk today is about that. So you have quantum computing. So the many quantum domain of the second revolution concerned by this are quantum computing, quantum communication and networks, quantum cryptography, quantum key distribution, quantum sensing also. But here we will not talk about quantum sensing, but the three other ones are concerned by what I will tell today. So in terms of activities, so we use what happens at Links to do some presentation or to invite people to present something. So here you will have the list of the seminars and reading groups at Links that are concerned by the sessions that are concerned by quantum systems in general. So about the seminar in gray, I will not go back there to that. It was presented last year. But then since the last reading group, in October, there was a presentation by Jan Birch with Michel Barbeau from Carleton University and Joaquin Garcia Alfaro from Telecom Sud Paris. So yesterday, so Jan is in the room, and yesterday he presented a poster on this topic. But I will tell a bit also during my presentation today about this work. Then I presented a paper that we published in GlobeCom last year, something about the authentication in quantum key distribution. So it's a work with my colleague. So for the publication, I presented it at Links, but for the publication, it was a work with my colleague Rémi Varlot. And we also invited Marc-Olivier Renoux from INRIA, who presented a very interesting aspect about the Bell theorem and the fact that we need complex numbers in quantum mechanics. Real numbers are not sufficient. And for your information, we will work more in the future with Marc-Olivier Renoux. We will have two PhD theses with him and Nokia Bell Labs starting end of this year. There are some sessions on the reading groups. So the one that have already been presented last year, so I will not go back to them. And there were 3 sessions on quantum aspects, quantum networks in general, or quantum computing also in the reading groups. The first one was by my colleague Rémi Varlot, who introduced quantum networks for people who knows classical networks but do not know quantum physics. And then I presented a tool that is really interesting to understand and to try to manipulate to better understand quantum computing and also quantum networks in some aspects, which is called QUIRK. And so I use two of the reading groups to present that. There was a first session about the basics that was in practical networks. And the second aspect, I tried to present few quantum paradoxes using this tool to show that how this paradox work in and why it works like this. So this was presented during the theoretical network theory reading group. For the publication in 2003, there was two publications. Sorry. The one from Jan Burge, Michel Barbeau, and Joaquin Garcia Alfaro about the quantum algorithm for Shapley value calculation, and the one with my colleague that I presented to Globcom this last year about the authentication through error estimation in QKD, quantum key distribution. And for the two, there was a link seminar. And in 2024, I was invited in the conference about communications circuits and systems, and the topic of my invited talk was about the transition from existing QKD system to future quantum networks. And Jan Burge with Ming-Tong Mai and Michel Barbeau also presented at the same conference something about the permutation, the dispatch circuit design for quantum permutation path symmetric encryption. I will talk a bit more now. I will talk a bit more on the three first publications now, but I will not go too much into detail because I would need at least three more time to present all this in details. So the first one I will present is the one of the work of Jan Burge, Michel Barbeau, and Joaquin Garcia Alfaro. So the context is about the Shapley value calculation that helps. This is something. This is a concept that is used to try to explain machine learning. So if we can have something that is fast in terms of the computation of the Shapley value, it will help in explainable machine learning context. So first, what are Shapley value? The Shapley value is something about a cooperative game theory. It is something within the theory of cooperative games, and the concept of Shapley value. So, as I told, is something that helps to explain machine learning models. Why they to try to find to be more precise, to try to find the features that are the most important to get the final results in the quantum in the machine learning process. So Shapley value is about some players and players. We have a value function, a gain function that gives a value of gain for each subset of the set of players, and it is called a gain. And Shapley value is something that it is a distribution function of the gain that is the fair in some specific properties. It's something that give a fair partition distribution of the gains for the winning the set of all the players. So it verifies several specific properties that one should expect to have a fair such a fair distribution. And this function has a given. I will not go too much in the details of the formula. There is a way to calculate this Shapley value, and but this way, the way it is calculated is a bit complex because you need to go through almost all the subset of the set of players. So when n is high, is big, it's a bit difficult to calculate it. What is also interesting, and it is more, at least for me, it's more easy to explain it for voting systems. So if you imagine a voting system in which the electors, the voters are different powers, so different number of voting ballots, then the Shapley value is a way to estimate the power of each voter, depending on the number of votes each voter has. So we have n voter with some weight. So the number, it can be an integer or not. You can also use something that is not an integer, but if it usually it is an integer, it's the number of votes each voter has, number of ballot each voter has. And for each a coalition wins the vote if the sum of the weight of the voters is above a given threshold that is called a super majority. So it is the majority if it is half, a bit more, strictly more than half of the sum of the weight, but you can have thresholds that are a bit higher. This is why we call it a super majority. And we can model this with the comparative game theory as described above. You simply set the gain function as equal to 1 if the subset of voters win the election. And then what we see is that in the formula of the Shapley value, it can be interpreted as a kind of average of this differential between the fact that a given coalition plus a voter win, and we compare this when we remove the voter that is labeled I here. So we consider the voter in the coalition or outside, and if it make the coalition win because he's here or lose if it's not here, this explains that it is it can be interpreted. The Shapley value can be interpreted as an indicator of the power of the voter I in the whole set of voters. So as I said, it's quite complex to compute because you need to evaluate. If you want to do it classically and naively, you need to evaluate 2 to the power n values of the gain function. So the question is, can we have so the problem addressed by Jainberg and his co-author is to find a quantum algorithm that computes the Shapley value in a faster way than the classical one. Just take the time, or it's okay. So the contribution is about an algorithm that computes the Shapley values using quantum algorithms. So yeah, there is the design of the quantum algorithm. So I will just describe at high level. So what we want to compute is this formula. So it's a weighted evaluation of the gain function V, considering voter I and compared to without voter I for each coalition. So the distribution is a special beta function. So we need to have something in the quantum algorithm that calculates this. Then we need to calculate the sum when the voter I is not in the coalition. So we need to remove to consider the fact that I is not here. So we use some rotation gates to do that. And then we need to implement the summation, the weighted sum of the gain function. In blue, we have the case where the voter I is added, and then we need to implement the subtraction of the two sums, and then evaluate the probability. And this can be done with, for example, with the quantum version of Monte Carlo. And this will give an approximation of the Shapley value. So I will just to show you that. So I discussed after the session. I discussed with Yain and Birch and Michel Barbeau and Joaquin Garcia Alfaro, and I just want to try. I hope it's okay. Yeah. So I have implemented the circuit. So I do the implementation for a simple case with 3 voters only. So it can be easily calculated because the number of voters is quite high, quite low. So each voter, I will just try to. No, it doesn't work. Maybe. No. Yeah. So it's a case where A, B, C have power 3, 2, and 1. And we have a supermajority threshold of 4. And if you do the calculation with classical, in a classical way, you should find 2/3, 1/6, and 1/6. So I have the quantum circuit here. So it is something. I will not go too much in the detail, but just to say that there are some blocks that do the trick. So I do not see. So the E2 gate is something that calculates the distribution, I think it is the beta, the special beta function distribution corresponding to the fact that we have n-1 voters, and so we should have, you should implement this distribution. Then you have the rotation, and then you have a first block here that calculate the sum, removing because you have this rotation. We use here this rotation. You are removing the voter A here, and we compare to the threshold of 4 of the supermajority. Here we have the same sum, but without removing voter I. This is why we use the control here that are different. That is different of this one. In this one, we removed A, and here A is included, and we compare to the threshold A here. And then we do. So the difference is easy to implement. It is a control anti-control on classical bits, so it is really easy to do. And we find the 2/3 value that we expect. If we move, so the fact that A is removed, I lost my mouse again, is here. Yeah. So here we by putting the note here, so the bit is the qubit is set to 1. It corresponds to removing A. If you remove B, you see that the value here change. It's a bit small. I hope that you can see it. It's 1/6, and for C it's also 1/6. Here, the gate that is used is just a matrix. It is easy for 2x2. It is easy to implement to set in this simulator. But we can also have so what Jan Birch and his co-author did. They also do give a good approximation of that, which simplify the calculation of this matrix, and this is using this one. So it is on the trick that they use correspond to this matrix, and you see that for A it was 2. So here it's almost 1/6. It's a bit different, and here it's almost 2/3. It's a bit different, but this gives a very good approximation. Okay, I will go there. And this is the second part of what they do. They give an efficient approximation of the special beta function probability gate by having some tricks. I will not go too much in the details. So there was these 2 contributions. Now I need to. I will present 2 other works. The one that I presented in the GlobeCom, and it's a work with my colleague Rémi Varlot. It was about authentication of QKD. So First, I will introduce shortly QKD, what it is. You have different quantum protocols, but in this paper, we were interested in BB84, proposed by Bennett Brassard in 1984, which is a prepare and measure protocol. So Alice prepare qubits in state randomly, so with uniform random distribution. She chooses to send qubits that are called 0, 1, plus or minus. F maybe between inside in the middle to trying to intercept what Alice and Bob are doing. And Bob does some measurement on some axes in the Bloch sphere, which is a representation of the qubits. So if Bob measures in the z-axis, he will measure either 0 or 1. If Bob chooses X, the x-axis, he will measure the qubit plus or minus. And so if Alice sends 0 or 1 and Bob measures with Z, he will measure exactly what Alice sent. But if Alice sends plus or minus, and if Bob chooses the wrong axis, Z, then Bob will measure 0 or 1 with probability 1/2, 1/2, and not with probability 100%. BBM 92 is another way. So it's again Bennett and Brassard, but with a third author, Mermin. And it is in their paper in 1992. It is based on entanglement. So an entangled pair of qubits is created somewhere in the middle. It can be in the network. It can be close to Alice or close to Bob. Anywhere between Alice and Bob. And then Alice and Bob do some measurement according to some randomly choice and independent choice of Z and X axis. So in terms of correspondence, to explain what will be used for the QKD, one can encode the fact that so in Z you measure 0 or 1, and in X you measure plus and minus. So if we set the bit value M equal to 0 or 1 corresponding to Z or X axis, and if we set the measure value to 0 or 1 if it is when it is Z axis 0 or 1, and if it is X axis plus or minus, you have this correspondence in terms of bits that can be manipulated in quantum key distribution. So for both protocols, BB84 and BBM92, we have the same property, quantum rules that applies. If Alice and Bob choose the same axis, then they will get the same value B measured or prepared in the BB84 for Alice. We have B for A equal to B for B with 100% probability. If the choice of axes are different, then we have the equality only in 50% of the case. In the other 50%, the bits are inversed. And of course, for QKD, what is interesting is that if Alice and Bob choose the same axis, you have something that is random. In the middle cannot know what has been sent by Alice in BB84, or because of the quantum nature of the Bell pair in the BBM92, the F will not be able to know what Alice and Bob will measure. So what I wanted to say, it is a way for Alice and Bob to create a shared secret key without communicating in the link of quantum communication, without communicating this bit value, the exact bit value. It is hidden by the quantum rules that applies for this quantum communication. I hope I'm clear. It's not so easy to explain for people who do not know quantum physics. So what is important is that in all these QKD protocols, Alice and Bob need to use classical channels to exchange information, not on the created secret key, shared secret key, but on some aspect that will help them to derive this shared secret key. What they need for example, what they need to know is they need to know when they choose the same axis. This gives no information about the bit value B, BA and BB, but for the eavesdropper E, which is outside, which try to intercept the communication, but it will tell Alice and Bob that they choose the same axis, and so they can use the bit to create the shared secret key. So this required classical authentication of the with today's solution. This required classical authentication mechanisms for the quantum classical channel to avoid the man-in-the-middle attack in the both classical and quantum channels. Without, but Alice and Bob may not know if they are talking Alice does not know if she's talking with Bob, and Bob does not know if she is talking with Alice. So this is really required because if not, Alice may believe that she's talking to Bob, but then she will talk with Eve, and this will break the key distribution creation secrecy. So the issue is one of the issues is this authentication may involve a third party, or they may use the authentication mechanism that are used may be broken in the future with some not yet known solution. So it can be unsecure in the future. So the question is, can we avoid the classical authentication mechanisms for QKD by using quantum physics? And this is what we proposed in this paper published in GlobeCom. So I will try to speed up a bit now. So what we propose is to Alice and Bob will use a pre-shared key to encrypt part of the classical channel that is critical for that. Of course, the pre-shared secret key will be smaller than the final secret shared key that will be created by the QKD protocol. We use one-type-pad encoding, so it is perfectly secure in terms of when we consider information theory and the results of Claude Shannon in 1949. And because the goal is to create a longer key at the end, and part of this longer key can be used later to create a new longer key later. So then to start the QKD exchange between Alice and Bob, we need an initial pre-shared key, but then by using QKD in different steps, in different rounds, they will be able to create a longer secret shared key by using each time by using the QKD that was used in the round before. So we proved that it was secure, and there is the details on the article. About the invited talk I gave this year in ICC-CIS, it was about the transition from QKD to future quantum networks. Sorry, it's not. There are some problems of printing in the screen. It's not like this on my PC. So there is a problem with Shor's algorithms with the current RSA crypto system that can be broken by the future quantum computer using Shor's algorithm. So we need new cryptography systems for quantum safe communication. Nowadays, two families of solutions are investigated. First one is about post-quantum cryptography, which is classical crypto systems that are quantum safe when we consider Shor's algorithms, for example, and quantum key distribution that are quantum safe quantum crypto systems. in terms of secure quantum communication, and what is feasible today? QKD is commercially available. We can, but on short distance, 100 kilometers. The problem is to extend this distance, and what we first can use trusted nodes, so links with less than 100 kilometers, and then nodes that we need to trust, because we go back to classical processing to extend the reach of QKD distribution. And there are some existing field trials on that. And for the future, one can use, could use quantum internet, but today so the interest is that we do not need trusted networks. And another interest is also the application is not only QKD. We can also use quantum networks for distributed quantum computing, delegated quantum computing, quantum consensus, and so on. There are some research required both in hardware and software. And the most blocking point today is the hardware part. The technology is not yet available for the quantum buffers and integral swapping and qubit transduction between mature qubits in quantum memory and flying qubits in fibers, flying qubits being photons. I will skip this part. It's about comparing PQC and QKD. What you should retain is that it's not really a competition. It depends on the use case. In some cases, QKD is better adapted. In other use cases, post-quantum cryptography is enough and better to use. And this is the slide to conclude. The people that are involved in LINX as members are Joaquin Garcia Alfaro, who collaborate with Michel Barbeau, Evangelos Kranakis, and Jan Birch at Carleton University. Jan Birch is currently with us as an intern at LINX, and he will he should be very soon a PhD student of Joaquin. So Rémi Warlot and myself from Nokia, we launched an exploratory research on quantum networks. And we will have very soon 2 PhD students to work with Marc-Olivier Renou at INRIA, who I talked in the beginning of my presentation about his work. And we also have some interaction with the ecosystem in Telecom Paris, INRIA, and also Lipsys, with a team in Lipsys working on this topic. Thank you. I was too fast, or maybe it was too complex, too complicated. Yeah. Don't hesitate. Yeah, Rock.
So then you pass the catch box.
Okay.
Catch box.
So I'll ask you the same question I asked actually yesterday. So you presented a talk that was about essentially quantum security. And the term quantum network is sort of much broader than security. So are there other sort of potential problems that requires quantum solution in the networking space that you can sort of potentially point out?
So this is what I just said, but it was a very small in my talk, a very short time. So for example, in the invited talk I had this year, so I really focus on the quantum security, quantum safe networks, and with using QKD. But what is important to know is that quantum networks can do more. This is what I wrote in this slide. There are other quantum applications than QKD for quantum networks. Distributed quantum computing, but this requires to have quantum computers today to do that. But if you have quantum computers, then you can imagine to have some networks in which the quantum computer chips are connected in a network to increase the size of the quantum computation. You can have also delegated quantum computing. So in this case, you need to send some qubit states to the quantum computers, and then it will give you back some results that that depends on the initial quantum state that you will enter in the quantum computer remotely. Quantum consensus also. So it is the other name is quantum Byzantine agreement, in which there are some quantum algorithms for that are faster than the classical ones, and maybe other ones. Quantum sensing, apparently there are some interest, but I didn't look too much inside it. I hope it answers your question. And in what I presented, there was also the calculation of the Shapley value by Jan Burge and his co-author. That is really a quantum computing algorithm, which has nothing to do with quantum networks.
Any further question? Okay, thank you, Ludovic.